So what does numerical oscillations, or where do they come from? So in our simulation, we have some voltage source, our RL components, right? We have a voltage crossing over this L component. Ours, they're easy. They're linear. They don't have the differential responses. So that component's fairly easy. But we're applying at some time a voltage at time 0 that's consistent. And then we have our current. So we've closed the loop. So this current source would be, for instance, your load. And this voltage source would be, for instance, your simulated or your modeled example. So you have stable voltages, stable currents in this context. We then apply some disturbance to a value of X, right? So the current's gone up. Let's say, for instance, you have your load. The load has changed, right? It's gone down in resistance. It's increased its power draw, whatever it might be. In response, we have to calculate what's going to happen from this. We'll get its numerical ODEs, and our step size is constant, right? So we have a consistent time step. So we calculate the difference, and we're going to end up, because here we're using just like essentially a first order approximation. We're using it for illustrations. This is going to be the most unstable, but even if you add more orders to your numerical solver, you can still, it makes it more stable, but you also have to spend more computational resources, so it's slower, right? There's always a trade-off between the two. So we go through the math, we end up with some y, because the initial value of 0 goes through. It then has to calculate the next step. So it's gone up to some value y. It does the calculation again. We run it through. Again, it's x minus x. And then it gives us negative y, because we're using just trapezoidal here. So it's really just the most straightforward one. And now you can see this is going to repeat over and over and over and over, where we're going to continuously get the inverse of it. And now you're going to just get this numerical bounce back and forth because this step size is too aggressive, right? So this is a very simplified example using just the trapezoidal rule, but this is the fundamental problem. When you're trying to solve the numerical equations, if you introduced another step here, as this change happened, you'd be able to stabilize it because the value of x is changing. But in this case, from the perspective of the simulation, it's a step jump, and it can't manage the response to that. This is called numerical instability, so we have to resolve that. So this is a key piece when you work with PHiL systems. You need to be aware of that kind of numerical instability. The nice thing is, if you just have a voltage source, like an ideal voltage source or a grid, it can be more stable. But this comes up when you start to deal with PHiL, having to encounter this. You can also, for instance, increase the order of the ODE solver. That's going to help stabilize things, but the trade-off is it's slower. It takes more time for it to run. So there's a couple different options. For instance, we can add a snubber essentially over it, or a damper over this section. So we add a capacitive component that's going to counteract. The trade-off here is you lose some accuracy. You know, your model is going to have this snubber component or other artificial component, but what it will do is it'll help essentially balance it out because it adds in that component. So that's the first option. We can also add in across the two sides, again, a capacitive component here that's also going to act as a snubber basically to suppress those oscillations. So you lose a little bit of accuracy, but you end up with a more stable simulation. Or you can add in filtering. So you can add in, for instance, filters that manage those high frequency changes and convert them to lower frequency. So that way your solver has more time to respond and actually maintain stable signals. And then the last step is just make your simulation time step smaller. So a step change becomes a gradient. If you can make it smaller, that's great. But oftentimes that's going to be a trade-off of how big a model can be. And then this goes into, again, some other components. So this goes into, let me just go down here to the actual, I'm not going to go through the full control mathematics because this is, again, a bit of a longer section. But the other option is you can change your control loops interface. So instead of just directly inputting it, you can actually change the interaction between your simulated model and your real system. And you can add in different kinds of transformation algorithms. They're called interface algorithms. And I think there's a slide that I'll give you the kind of the top level of it. But so these are some different transformation methods that are available. These are in the literature that will be in the slides. If you're a big controls nerd and are curious about this, you can go ahead and take a look. But the most common one, and the one we typically use, is the ideal transfer method, where we just directly send the references. But then you can get into, different kinds of damping modifications, transmission line modules, time variance models, all this kind of stuff. This was the focus of Sebastian's PhD, is how do you stabilize and improve simulations. The next section here overlays some kind of broad ideas of these different methods. So yeah, going through the VITM method, which is what we use here, it's high accuracy, it's got good dynamics and good bandwidth. The trade-off is it's not the most stable and it's limited in the scope of what it can do. However, for most people, this is acceptable. This is a perfectly good algorithm. It gets the job done. And then you get into others that have, for instance, like a filtered approach. So we add in some dampeners. So in this case, it increases your stability and the range of systems you can simulate, but you lose out on accuracy because you're filtering, you have less bandwidth, and you also lose out on some high frequency dynamics. But that might be important to you if you need a very stable system. For instance, in short circuit testing, this sometimes comes up where you don't mind losing a little bit of dynamics, but you need it to be very stable in particular configurations. And again, these different applications all come from there. And then, yeah, here's the references for the slide are all listed here. So if you want to go through. So this closes that loop. So we have our simulator, our power amplifier, and the interface algorithm happens between the two here. So how do we manage those signals? And then the power amplifier connects to the real system. They interact, and then measurements from the amplifier go back. So those current and voltage probes, they go back into the simulation, and that gives us the results. So yeah, we're kind of where we are is right now improving our modeling and interface algorithms so we can get better results, having to compromise less. We're trying to do better turnkey solutions because PHiL is still a relatively new technology, and it requires you to understand both electrical engineering, control engineering, and simulations. So that overlap of skills is not as common in the industry. And then we're also increasing our specialized and customized beds. So we're doing, for instance, HVDC kind of simulations with power equipment, MMC topologies, if you're aware of those, modular multi-level converters, those kinds of advanced technologies that people want to simulate.